Hello to you all ANSYS users and CFD enthusiasts. Welcome once again to CFD Lands with our free products. In this try and problem, we're going to simulate the tube bundles, including the heat transfer analysis over a specified domain. The point is that in this simulation, we're going to actually get to know about periodic boundary condition, which can be very helpful when we are dealing with a problem in which a repetitive pattern, or but let's say the error of the geometries are included. So before doing the simulation steps, I kindly ask you to like and subscribe our channel to be notified about our latest option. So let's start by drag and dropping the fluid flow with the flow software. I want to create my model inside the design model. So by right click on the geometry, you can find the new design model module. Label. So as I mentioned in here, in this simulation, we're going to get help from periodic boundary condition. So what we have to create is just a section of a model. And also the tube bundles could be repetitive along the x-axis and also along the y-axis. If I start my drawing, you would better see what I mean from this. So first of all, I want to change my units to centimeter because I want to specify all of my dimensions based on centimeter unit. My geometry will be put on the XY plane by creating a new sketch, which is called the sketch one. I can normalize my view, zoom a little bit to have this dimension. As you can see, the scale is between 0 to 5 centimeter now. And I can start my drawing. Picking up the rectangle tool, I can start from this origin and draw a rectangle like this. So my actually tubes will have a circular cross section. This is why the circle pattern can help us to draw the first tube and then the other one down here. So this is just half of, but it's a part of my geometry model. And these patterns will be repetitive along the x-axis on the right side and also maybe on the left side. And the other thing is that it's symmetric along the y-axis. So instead of creating a full circle, I can just consider a half of it. So I need to subtract the other parts, which are the extra parts. For this, I pick up the trim tool from the modify tab and then simply click on this section, these extra lines, and also do the same thing for the other tube. And as you can see, all that I'm modeling is just half of the tubes. And then for two tubes, I just half of the this domain and not considering all of it. And this is the benefit and what a CFD engineer must take in when it gets to the stimulation part. We need to actually manage the computational costs as much as possible. Very well. So let's complete the dimensions. From the dimensions tab, I pick up the semi-automatic option. So the software first of all asks for this tube diameter and then the other one, and then the height of my rectangular domain. And it's time for these actual distance, but I don't need this. Instead of this, I right click on exit and then taking up the horizontal tool, I hold down the control key to specify the distance between the center of my first tube and this elet. And also the same thing for the other tube. So based on the actual dimensions that I have, this part is 1 millimeter distance. And of course, the diameter of each of these tubes is 1 meter. So it asks for the radius, I guess, yeah. So I need to put 0.5, which is half of it. And then the same thing for the other tube. And for this distance between the second tube and the inlet boundary, it should be 3. No, it was just a height L3, which stands for the height of my rectangular domain. So I have to decrease that to 1 centimeter. And then the distance between the second tube and the inlet boundary is 3 centimeter. So I guess there's some specifications that needs to be added. This is 1 meter. And yeah, I guess we haven't specified the distance, or better say the length of my domain. So I can pick up length per distance. hold down the control key, select these two vertical lines, and specify L7, which stands for the length of my domain. In total, it is 4 centimeters. And now I can say I have a fully constrained sketch. It's time to convert it into a surface, or let's say a fluid domain. And from now on, we will work with the surface body, which stands for our geometry domain. So I quit Design Modeler software and double click on Mesh to open ANSYS Meshing. All right, in ANSYS Meshing, we've got 2 main missions. Our first and most important mission is dividing a computational zone into different computational cells. And then in second mission, we have to specify and name all of our boundaries. So let's begin with our first mission. As I click on Mesh, you can see our Physics Profans by default is on CFD, which is correct. And then for the element size of our domain, we can have a general specification in here. But instead, I want to pick up the face selection tool, select my one and only surface body, right click on Mesh to insert a new sizing. So let's begin with 1 millimeter for this actually discretization of our domain. I want to put 1 millimeter. And simply as that, we can generate our first grid to see the elements. So this is our initial grid. Maybe I can just apply method 3 to have triangular cells. And in order to do so, this time I insert a method, select the surface body, and instead of quadrilateral dominant, I want to change it to triangles. Simply as that, if I update it, you can see the new mesh. But of course, these cells are very large comparing to the domain size. So I have to decrease the face sizing to, for example, 0.1 millimeter. And if I update it right now, you can see what will be the result. Very well. So it sounds like a perfect mesh right now, but the point is that I'm going to have hot tubes with 400 Kelvin temperature. So there should be a kind of separation and establishment of thermal boundary layer on them. This is why this region very matters. And I want to actually employ a boundary layer on them. So right click, in this time insert an inflation. And for the domain, I simply pick up the face selection and it's like my region. And then for the boundaries that I want to actually create the boundary layer on them, I select these 2 walls of the tubes. So I want to use this most transition, considering 7 layers, for example, with 1.1 perfect. So now let's see what we have. Very well. So this is our bound layer. If I zoom a little bit, you can see the transition from the first layer up to the 7th layer, and then the other elements, which are triangular. So I guess this mesh is going to work, and we can say that our first mission is completed. Now it's time to label all of these boundaries. I start by selecting this inlet and right click to create a node selection for it. I want to call this our inlet boundary, and then the other one would be our outlet. Of course, these boundaries are going to be a periodic boundary condition, but for now in ANSYS meshing, we have to label them. So from this triangle, you can see we specify the inlet and outlet. This is the symmetry wall from the upside. So I call this, for example, the symmetry up. And then the other side could be the, oh, my bad. This could be the symmetry down. And then the 2 walls. I select them both together and create a single name for them. For example, 2 walls. The boundary condition for these 2 walls are the same. This is why I actually put a single name on them. So in total, let's check them together. Inlet outlet, these symmetry walls. and also the two walls. I guess we're done inside ANSYS meshing, and by just clicking on Update button, we can make sure that the translation to Fluent software is successful. So let's quit ANSYS meshing and double click on Setup to open the solver. So due to high accuracy, I wanna activate dual precision in order to have the calculations up to 16 decimals. And based on the system that you're using, you can employ a higher number of processors. For example, for my system, I put 12 processors. Very well. Finally, it's time for the solver settings. On top, the general settings, which include the general assumptions of our governing equations. First of all, we're going to employ the Crash-Bit solver, which means that the density changes inside the governing equations will be ignored, and this is used whenever we're dealing with incompressible fluids. In our current simulation, we're going to have the volatile liquid as the working fluid. This is why the pressure-based solver will work. And then, of course, we want to simulate in the steady-state transition obviously state, and this is why I don't want to change it. And it's time to actually expand the model section and double click on energy to activate the energy equation, because they've got heat transfer, and this simulation also include the heat transfer analysis. This is why we have to solve the energy equation along the molecular equations. And then for viscous turbulence model, as you can see, we have several options, but what is important in this simulation is that we expect the formation of circulating zone after each of the tubes, and also the bound layer, the thermal bound layer establishing over the tube walls is important. This is where the K-omega system model can help us to capture all of this flow behavior. Very well. So I guess we don't have to do anything in the model section. So I close it. It's time for the materials. And as you can see, the area is clearly defined, but a working fluid now is water liquid. So I have to add it from the Fluent database. And if you scroll down, you will see the water liquid and simply copy that. And from now on, we have two different fluids that are defined in the software, and we can employ on our computational zone. In order to apply it from the self-zone condition, you have to find your one and only surface body. And by just clicking on Edit button, you would be able to change the material. So as I said, we are going to use model liquid passing over the bank of tubes. So I apply it and close it as well. And now for the boundary conditions. So let me show you the initial boundary conditions. As you can see, we've got inlet and outlet as we defined, and based on the names, automatically the software detected them as the velocity inlet type boundary condition, or for example, the pressure alpha type. But we already know that we're going to make them periodic, and this is why in this part, in the console point, I want to start commanding. So first of all, I put down the mesh to see what are the commands. For the mesh, we've got plenty of options, but what I need in here is the modify zones. So I copy that and pasted it here. And then for modifying zones, we've got plenty of options. But once again, what I need to find is making periodic. So let's find it. Yeah, there it is. So I simply copy that and paste it in here. And as you can see right now, the software asks for the periodic zone ID, and you may wonder what is ID. As you click on each of these boundaries, you can see it is there is actually an ID dedicated to this zone, or let's say boundary, and you have to put it in here. So our first periodic zone is ID 5, which stands for our inlet, and then the shadow zone is our outlet, which has the ID of 6. So I put 6 in here, and then we know that there is not rotational or periodic, it is translationally. So I put no in here, and then create periodic gap zone, yes. And finally, auto detect translation lecture, yes. In this way, we can modify these boundaries, and you can see right now we've got periodic boundaries. And then from the periodic conditions, we are able to specify the boundary conditions. So I want to specify a mass flow or that. So I change the periodic type to specify mass flow. And then for mass flow rate of incoming bottle liquid, we have 0.05 kilogram per second. The flow direction regarding the origin and the actually what they created inside the molar. We already know that the flow is coming from the left side through the right side, which is completely normal to our inlet boundary. So the flow direction keeps with 1 for x. And then I'm not going to change anything in here. And of course, the temperature of the incoming water is 300 Kelvin. And I'm not going to change it. So for the symmetry boundaries, due to actually selection of the name, the software automatically once again detected them as the symmetry boundary condition. So it acts like a mirror, and in these actually yellow boundaries, which we call them symmetry down and symmetry up, wouldn't have any shear stress. It's like just like a mirror, and it acts like a mirror. For better visualization, let me show you that from the View tab, you're able to have this mirror to have the full computational zone. And now you can see what I was mentioning. It is somehow symmetric from up and down, and then periodic from left and right. And for a very last boundary condition for the two walls, we have to apply a 400 Kelvin temperature. So I'm not going to change anything in the momentum tab. These are stationary with no shift condition. But in thermal, I want to apply a constant temperature of 400 Kelvin. There you go. So I guess we're done with setup section, and it's time to delve into the solution for actually handling the pressure velocity coupling. ANSYS Fluent offers you 4 different schemes whenever you're using pressure-based solvers. So what we're going to employ in here is a simple algorithm, which is one of the mostly used algorithms when it comes to steady-state simulations. It is one of the segregated algorithms, and it is using an iterative solution. And what you need to know about it is that we're going to have and calculate the pressure correction term and have a repetitive action in order to reach the conversions. And then for discretization of the equations, first of all, the pressure gradient term, we want to use the Presto model, which is one of the most comprehensive models provided in ANSYS Fluent. For momentum equation, we use the second order often due to its higher accuracy. And then I don't want to change the tool kinetic energy and dispersion rate. The first order up and will work, but the energy equation matters. And this is why the second order argument is kept. And now it's time to check the residuals as our primary convergence criteria that you can find beneath the monitor section. So in each iteration, we will have the residuals reported down here in the console part. And 2 consecutive iterations, we show you the difference between 2 consecutive iterations, actually regarding a calculation of each of the momentum and energy equations. So whenever these values that will be listed in here during the solution reach these absolute criteria that we define in here, the software automatically detected the solution as a converged one and it stopped the calculation. So I want to keep with the default values, but mention that for energy equation, we always have a lower value and lower absolute criteria. And this somehow makes it hard to reach for this periodic simulation. So this cannot be reliable, and you cannot just trust the residuals. You have to monitor a critical parameter yourself, and whenever it gets to constant value, you can stop the solution yourself. So in order to monitor, for example, the temperature at the outlet, or let's say, for example, the velocity at the outlet, you have to define a new report. So I want to start by defining with area weighted average type of report for the outlet boundary. And I want to monitor the velocity at the outlet. So I call this report B outlet and select the variable, its velocity, and my boundary, the outlets. I also monitor one parameter regarding the energy equation, like the temperature at the outlet. So I call this T outlet. And then from the field variable list, this time I select temperature and then the outlet boundary. So from now on during the solution, we will monitor the temperature and velocity at the outlet boundary. Very well. So I guess we're done and we can go through initialization section using the standard initialization method to have and put the initial guess into the governing equations. And regarding the initial values that we put in here, we can have the initial state. Very well. So I guess the case is completely ready to be simulated. Then from the run calculation section, I'd put down 5,000 number of iterations and start the calculations. So let's see what do we have. As you can see in here, during the solution, we can have and monitor the temperature at the outlet boundary because we define the report, and also the same thing for the velocity at the outlet. And if we check the results, you can see for now, just after 100 iterations, we cannot see a converging pattern, but we have to wait for it. So let's wait for it to see how it goes on. There you go. So the solution is converged based on the parameter that we set in here, the convergence criteria. So if you check the reports, you can see that the velocity at outlet does not converge, but about the temperature, it somehow gets to a constant value, but we have to go on a little bit more. So this is why we always say that do not trust the residuals. These cannot represent and guarantee your convergence. So this time I want to uncheck all of these and convergence criteria and instead do it myself. I will start the solution whenever I guess this is ready. And there is one more thing that I wanted to mention. It's about the energy equation, which is colored in blue. You can see after 100 iteration, it just goes on and it does not shows a clear pattern to a better convergence. This is where the under-relaxation factors step in. So if the dog look on controls part, you can see under-relaxation factor that can help us manage and control the solution. This somehow relates to what we're doing with correct number. And if you don't have any information about it, it's essential to check out our website, the blog section, in which you can find an article about the quant number. So this time I want to decrease the under-relaxation factor for momentum equation to 0.5 and for energy equation as well. So one more time, I initialize with this standard initialization method and start the solution from the outset. All right, so the solution is completely converged and I stopped it after about 2,250 iterations. You can see the temperature plot that it reaches a constant value and also the same thing for the velocity report at the outlet. So let's check the result together. To start, I want to start displaying the different fields such as the velocity field and pressure field. We can start by this pressure, and of course I want it over the domain so I don't actually change the settings. And if you see that, you can see the bank of tubes. But the most notable thing about this is that you can see the next row's effect on the last boundary of our domain. This shows that we could successfully model the periodic boundary. And of course, it goes without saying that at this stagnation point, we expect the highest amount of pressure. But if we change the variable to the velocity, it can show us better what is going on. The point is that you can see this is the stagnation point that is completely right in the front side of the tube, and due to its symmetry pattern, we expect it to be exactly in the middle. The other point is this vague region behind each of the tubes that we expected, and this is actually one of the main reasons that we employed the k-omega system model. And also the separation that is happening on the wall of the tube And the point is that due to the Reynolds number and also the high velocity of the incoming water flow, the expected to be happen somewhere before 90 degree, and it is completely, let's see. The other point is that that I want to mention in this vague region, we can expect some recirculating zone that can be monitored and displayed if we change the velocity into the stream function. In this way, I guess we can have it. Yeah, so let's just uncheck the field. Now we can have the contour bands. And yeah, there it is. You can see the recirculating zone that is established completely symmetric due to circular pattern cross section of our tubes. So one more important thing is that once again, from the inlet, we can see the effect of previous tube bundles on the next rows. So in this way, you can depict any variable that you're interested in. And I guess I forgot to mention the temperature field that can be helpful. These are the isotherms, these lines, the isotherm pattern. And as we already know that the 400 Kelvin is the temperature of the tube walls, but regarding the temperature of the incoming airflow, we expect a heat transfer from the tube wall into the water flow. The point is that in spaces that we expected the recirculating zone, it actually results in better mixing, and this is the main reason that we had the best heat transfer in these regions. So completely like this, we can have a quantitative report as we employed, for example, the velocity at the outlet. As you can see, it is somehow reaches 5 meters per second, and also the 300 Kelvin temperature that is coming in from this inlet boundary reaches above 307 Kelvin. And in this way, we can ensure how to actually arrange the area of our tube to get to the best heat transfer and also the objective of hydrodynamic problems. So I hope you find this tutorial helpful. Once again, like and subscribe our channel for more free products.